The last problem in the derivative section of our review is to analyze the graph of a function given by sine of 4 pi x. And in particular, we need to identify the intervals where our function is increasing, decreasing, concave up, and concave down. So first, let's start by thinking about where the function is increasing and decreasing. And I do that using the first derivative. So my first derivative, if I have a function given by the sine of 4 pi x, the derivative, f prime of x, will be the cosine of 4 pi x times 4 pi, which will write 4 pi cosine of 4 pi x. So notice that this is a product. It's a product of 4 pi, which is always positive, and the cosine function. And so I'm going to think now about the cosine function using the unit circle. The cosine is an x-coordinate, and it equals 0 when the angle is either pi over 2 or any 2 pi loop in addition to that, or negative pi over 2. Okay. Except that this time my angle is 4 pi x. So what we have is we will be equal to 0 for our derivative if 4 pi x, the angle, is pi over 2 plus 2 pi k, because there's any multiple loop of that. That's for the top. Or if the angle 4 pi x equals negative pi over 2 plus 2 pi k. So I'll solve for x, I'll divide both sides by 4 pi, and pi over 4 pi, or pi over 2 over 4 pi, the pi's cancel, I get 1/8, plus 2 pi over 4 pi is k over 2. And for our second set, we get negative 1/8 plus k over 2. So let's think what those numbers mean. If k equals 0, I'd get 1/8 plus 0. If k equals 1, I'd get 1/8 plus a half. That would be 5/8. If I had k equal 2, I would have 1/8 plus 2 halves. That's plus 1. So that's 8/8, so that's 9/8. So I'm just counting by 4/8. Alright. So if I do a sign analysis now, I have 1/8. And then I also have negative 1/8 from the other half of the circle. If I add 4/8, I get to 3/8. Then 5/8 from the top, and 7/8 from the bottom, 1/8, 9/8. Let's go back the other way, negative 3/8. So these are all the places where the derivative actually equals 0. And now we need to figure out the sign of our derivative, and we'll do that by thinking about values in between. So for example, 0 is in between here. And so if I put x equals 0 into my formula for my derivative, I get the cosine of 0. And the cosine of 0 is 1. 1 times 4 pi is positive. And so I've learned that on that interval, my derivative will be a positive value. Alright, so then next I might come here and say, alright, between 1/8 and 3/8 is the value of a quarter. And so if I plug a quarter into my derivative function, a quarter of 4 pi is pi. And the cosine of pi is negative 1. And so this gives me that I have a negative value in the next piece. And so as I go around in each of these apart. So here I have a half. If I plug in a half, 4 pi times a half is 2 pi. Cosine of 2 pi is positive 1. I'm back to positive. I see that I'm just alternating as I go around the unit circle, just at a faster rate. So there's our sign analysis, and now we just need to interpret. So we'll say my function f is increasing on each of these intervals, and let's figure out how we can describe the intervals where I'm positive. So let's see, I get 0 minus an eighth to a plus an eighth, a half minus an eighth plus an eighth. So if I think about counting every half, this next point on the far right, the center of that would be actually at 2 halves. And I could think of 0 as 0 halves. And here I'd have negative 2 halves. Sorry, negative 1 half. I have to do that right. 1 half. Then I can think of each of those intervals as looking like an integer half, so k halves, minus an eighth to an integer half plus an eighth, where k is 0, plus or minus 1, plus or minus 2, and so on. And my function is decreasing. Now we have to think about how to describe those others. Well, I might think about the same starting points, except I go plus an eighth to plus 3/8. So we're decreasing on k over 2 plus an eighth. That's my left endpoint. K over 2 plus 3/8 will be my right endpoint for the same values of k. K could be 0, plus or minus 1, plus or minus 2, and on and on. And so that is how we describe where my function is increasing and decreasing. To answer the second part of the question about concavity, we'll need the second derivative. So, second derivative of x. 4 pi is a constant, so we have a constant multiple, 4 pi. The derivative of cosine is negative sine, so it's negative sine of 4 pi x. And by the chain rule, I have to multiply by 4 pi again. And so my second derivative is going to be negative 16 pi squared times the sine of 4 pi x. And again, I have a factor in front that's a constant. This time it happens to always be negative. So I need to think about when is the sine function positive and when's it negative. Again, we'll do this using a unit circle. This time we're thinking about the sine function. And so the sine is going to be 0 when the y-coordinate is 0. So one way we could think of that is at either 0 or 2 pi. So here we have 2 pi k. And here we have all of our odd pi plus 2 pi k. So when I'm interested in my second derivative equals 0, I have my 4 pi x, that's my angle. It's whatever's inside the function is going to equal either 2 pi k for the right hand side, or 4 pi x is going to equal pi plus 2 pi k. And so when I solve for x, in the top example, I'll get 2 pi over 4 pi, that'll be k over 2. And in the bottom, if I divide by pi over 4, or 4 pi, I'll get a quarter plus k over 2. So if I think about the example of what kind of values this gives me, when x equals 0, k equals 0, I get x equals 0, or a half, or minus a half, or 2 halves, which is 1, or minus 1. I get all the halves. And in the second example, I get a quarter plus 0, or I get a quarter plus a half, so that's 3 quarters, or a quarter minus a half, so that's minus a quarter, or 5 quarters. So I get all of the odd quarters. So as I do my sign analysis for my second derivative, I'm going to have every quarter listed: 0, a quarter, a half, 3 quarters, minus a quarter, minus a half, minus 3 quarters. These are all the places where the second derivative equals 0. And I'm running out of space, so I'm going to clear a little space. Now that I know the spots where it's equal 0, I need to now look at the intervals in between, and I pick some points. So for example, in this interval might be the number 1/8, and so if I put x equals 1/8 into my derivative, 4 pi times 1/8 is pi over 2. So here I am at pi over 2, and the sign at pi over 2 is 1 times negative 16 pi squared. That gives me a negative value. So I've discovered that on that interval it's negative. And as I go around the unit circle, I'll alternate signs. Just to illustrate that one more time, 3/8, if I were to put that in for x, 3/8 will give me 3 pi over 2, which is down below. The sign is negative 1. Negative times negative is positive. And so I see that I'm alternately positive and negative as I go around the unit circle. Now that I know where I'm positive and negative, I can answer the question where I'm concave up and concave down. So my function f of x is concave up. Notice I'm not saying the second derivative. F of x is concave up on a typical interval. Let's see how we can describe it. The positive ones are all looking like integer halves, and what's on the left. And so I could write they're concave up on k halves minus a quarter to k halves. Okay. Just to reemphasize that, my intervals, each of these positive intervals, ends on the right at a half. Minus a half, 0 halves, 1 half. And so I put k over 2 to represent the right endpoint, and then to get the left endpoint I need to go back a half of a unit. So that's why I'm subtracting a quarter of a unit. So this is where I'm concave up. I'm concave up on this interval. Oops, how did I get the wrong color? As long as k is one of my integers. And I'm concave down on intervals that look similar, except this time the halves are the left endpoints, so k over 2 to k over 2 plus a quarter for the same values of k. K are my integers, 0, plus or minus 1, plus or minus 2, and so on.